The most famous scientist of all time, Albert Einstein, probably would not surprise you to know that Einstein won a Nobel Prize during his lifetime. What probably would surprise you is that it did not come for his work in relativity, but instead came for his explanation of something known as the photoelectric effect, which is a pretty simple phenomena. Turns out if you shine light on the surface of something like a metal piece of metal, if the light that you shine on that surface has enough energy, it will emit or eject electrons from that surface. Doesn't matter how long you shine the light on it. If the light itself has sufficient energy, electrons are emitted. However, if the light doesn't have enough energy, you could shine that light all day long and no electrons would be emitted. And I think one of the big takeaways from this and why it's such famous work from Einstein is that he had a unique proposal for why this is. We know that light travels as a wave, and at the time, the prevailing thought or wisdom was that that light was essentially continuous. A wavelength in that wave went on forever, essentially, or indefinitely. Einstein proposed, though, instead that the waves that make up light actually come in small chunks, kind of like we think of matter as coming in small chunks. And so rather than a continuous wave, you would have little chunks or what he called wave packets of energy. Now, I want you to imagine a scenario where you're being punched on the shoulder by a 4-year old, and that 4-year old punches you maybe 1,000 times. Even even one time doesn't hurt that much, but over the course of 1,000 punches, you're probably still not going to really be harmed at all by the punching power of that 4-year old. But if instead we replace the 4-year old with a 40-year old who hit you on the shoulder as hard as possible, it would probably hurt even just one punch. You don't need 1,000 punches. Well, likewise, Einstein said, it doesn't matter how many little wave packets we send towards the metal surface. If those wave packets individually don't have much energy, then no electrons are ever going to be ejected from the surface. But if one of the wave packets had enough energy that even one of them could eject electrons from the surface of the metal. These wave packets go by a different name today. We call them photons. And you can think of a photon again as just a little chunk of light energy um, that uh, that comes in waves, but also comes in large numbers if you turn on a light or um, or looking at the light that comes from the sun, what have you. We can actually calculate the energy of one of these photons very simply. Energy equals h nu. We know nu, we talked about it in our last class. Nu is frequency, and energy is something that we're going to measure in joules. H is the thing that we might have a question on. This is a constant. Many times, in order to get a relationship to work, we need to have some number, some unchanging number that allows the relationship to be expressed as an equation. And that's exactly what we have here with H. H is called Planck's constant. It's an unchanging number that delivers an equation that represents the relationship between energy and frequency of these little wave packets or photons. H is 6.626 times 10 to the minus 34 joule seconds. A strange number, no doubt, but it's what makes this relationship work. We also that know that nu, which is frequency, is equal to c over lambda, which is which is speed of light divided by wavelength. So I could change this equation if I wanted to E equals h times c divided by lambda. We're just making a substitution there. That's going to help us on the problem that we're trying to solve below. It says, what's the energy of a photon with a wavelength of 500 nanometers? Talked about it's useful to change nanometers to meters, and that the easiest way to do that is to replace nano with the power of 10 it represents, 10 to the minus 9. So we're trying to find the energy of a photon with this wavelength. So if I plug into my second equation, E equals hc over lambda, h is 6.626 times 10 to the minus 34 joule seconds. C is 3 times 10 to the eighth meters per second. And the wavelength, which is given here, is 500 times 10 to the minus 9 meters. If I look at my units, many of them cancel out. Meters cancel out, seconds cancel out. Let me go back. Seconds cancel out, and we're left with joules. So now all I have to do is get out my calculator, and on that calculator, I'm going to punch in 6.626 E, which is second comma, negative 34 times 3 E8 divided by 500 E negative 9. If you do that, you get 3.98 times 10 to the negative 19th joules. So each photon does not have very much energy at all. I would write the unit as joules, but you could also write it as joules per photon. And so you would need an enormous number of photons to produce a sizable amount of energy. All right, let's practice some of these problems, and we'll come back next time with a new idea.